So we're in the process of making up some ground on Dirac stuff, and today will be presumably be the last day we're on that part. I'd like to start the day with chiral fermions. A little bit of technology here and some interpretation, and so let's take a massless limit. Okay, then the Dirac equation is ID slash psi equals 0. There's another solution. Is ID slash gamma 5 psi is equal to 0, because gamma 5 gamma mu equals minus gamma mu gamma 5. So the anti-commutes, so you just bring it through, and it's also a solution. So we can take linear combinations. You take psi left is 1/2 1 plus gamma 5 psi right is 1/2 1 minus gamma 5 psi, and these are then also solutions to the Dirac equation. If you look at them, remember u of p is some normalization which doesn't concern us right here. Chi, it's sigma dot p over e plus m chi there, but as m goes to 0, this turns into chi sigma dot p over p chi. So if you then multiply to get a left-handed one, so u left is 1 plus, that's 1 plus gamma 5 on u, that turns into the following. It's 1 plus gamma 5 is a 1/2. 1 plus gamma 5 is 1 minus 1 minus 1, 1. And then u is chi sigma dot p hat. Chi p hat is the direction. This then turns into n over 2, 1 minus sigma dot p hat chi 1 minus sigma dot p hat chi, with a minus sign there. So both upper and lower are the same, so you've only got half as much information. But the other thing that's visible there is that if you use helicity basis, where sigma dot p hat, you quantize the spinner along the direction of motion, is lambda chi, where lambda is then going to be plus or minus 1. The u left, psi left is purely helicity. Lambda is minus 1. Psi right turns into purely lambda is plus 1. So it's left-handed helicity and right-handed helicity. Helicity against or along the direction of motion. So the handedness here refers to that. Okay. A little more generally, is there a question on this? These are projection operators. When the m is equal to 0, they don't project out helicity. They do in m equals to 0. So if we make gamma left is 1/2 1 plus gamma 5, gamma right is 1/2 1 minus gamma 5. These are projection operators. They satisfy gamma left plus gamma right equals 1. Gamma left squared is gamma left. Gamma right squared is gamma right. Gamma left, gamma right equals 0. Okay, I don't know how much to work that out. It's easy. It's not that hard to work out. If you do gamma left squared, it's 1/4. 1 squared plus gamma 5 squared, which is 1. And the cross term is 2 gamma 5. So it turns back into gamma left. Okay. So we can, even for massive fields, we can make the decomposition. Psi is psi left plus psi right with the same definitions. You know, psi left or right is gamma left or right on psi. Since it's projection operator, you can always do that. You should note that when we take psi bar left, okay, that's psi dagger gamma left dagger gamma 0. Okay. So it's okay, right? When we take psi bar, there's a gamma 0 there. Gamma left dagger is just gamma left. It's just because gamma 5 is Hermitian. So this is then psi bar gamma right, since 1 plus gamma 5 gamma 0 equals gamma 0 1 minus gamma 5. Since it commutes with all gamma matrices, anti-commutes with all gamma matrices, you pick up a minus sign there. So this is gamma right that sits there. Even though it's psi bar left, gamma right sits there. That's important for what we're about to do.
You didn't mean anything different by putting 0 and the superscript.
Gamma 0 is the same, is actually the same upper and lower. And so yes, I didn't mean anything. You're right. Right. Yeah, so remember, going from uppers to lowers, the gamma I changes sign because the I, there's a sign change there, but the zeros don't. Okay, but good, thanks, good point. Okay, so let's look at the Dirac Lagrangian. Okay, the Lagrangian is L is psi bar I d slash minus m psi, and we'll break each of these up into psi left and psi right. Okay. So the mass term, if we have psi bar left, psi left, from what we just worked out there, that's psi bar gamma right, gamma left, psi, that's equal to 0. So for the mass term, where m is just a constant, that there is no psi left term. If you have psi left, psi bar left, psi right, that's psi bar gamma right, gamma right, gamma right, psi, that doesn't vanish, so that stays. Likewise, the kinetic energy piece, the kinetic term, if I have psi bar left I d slash psi left. That's psi bar gamma right I d slash gamma left psi. But now this gamma right, as it goes through the d slash, becomes gamma left again, because the gamma 5 piece changes its sign. So this is psi bar I d slash gamma left psi, which survives. And psi bar left I d slash psi right. Again, psi bar gamma right d slash gamma right. That equals 0 by, again, the same trick. You pull this through, this becomes gamma left like up here. Gamma left times gamma right is 0, so it disappears. So the Lagrangian then that we wrote up there has the following form. It has psi bar left I d slash psi left plus psi bar right I d slash psi right minus m psi bar left psi right plus psi bar right psi left. So the mass term mixes left and right, but if the mass term were 0, then the left and rights are separate. So those little facts are important. The other thing in the massless limit there's two invariances. You can have psi left goes to e to the minus I alpha left, psi left, with psi right being unchanged, or you can have psi right goes to e to the minus I alpha right, psi right, with psi left being unchanged. Those are two separate invariances. So Noether's theorem tells us that there's two separate currents. L mu is psi bar left, gamma mu psi left, just forms of the left currents, is then psi bar and gamma mu 1 plus gamma 5 psi. And R mu psi bar right gamma mu psi right is the same thing with a minus 1 minus gamma 5 there. These both are conserved. D mu L mu equals 0 if M equals 0. Okay. And you actually know that from where we started. If I take a derivative here, gamma mu on psi is a solution, and gamma mu on gamma 5 psi is a solution. That's where we started that exercise. So that's true. For a later reference, we often will do this as V mu is L mu plus R mu. That's the vector current. The axial vector current is L mu minus R mu. Well, this is psi bar gamma mu gamma 5 psi. And with a mass, we still have d mu v mu equals to 0 because there's still one invariance. psi L and R goes to e to the I alpha psi L and R. If you do them both at the same time, they're still at invariance. But if I take d mu, a mu turns into 2im psi bar gamma 5 psi, which you get just by doing the Dirac equation. If you want me to do it, I can do it clearly. Yeah. I'm sorry. Why is this one equal to 0? This one is not equal to 0. Oh, it's not equal to 0. I'm sorry. Bad. There we go. Thank you. Yes. So this is not equal to 0, just like this guy is not equal to 0. So in each case, the chirale kills one combination. Thank you. Okay, so there's a bunch of stuff connected to chirality and masses. Let's take this time to do the Majorana mass also.
Are you,
Yeah.
can you make this bottom of that left slide visible?
Yep.
Flip back and forth.
Yeah. There we go. Sure. When we form a mass term, we form a Lorentz invariant combination. In the Lagrangian. Lagrangian has to be a Lorentz scalar, so psi bar psi is the Lorentz scalar. Likewise, psi bar I d slash psi is a Lorentz scalar. Now, you might ask how we know how we prove that. I haven't done it for you. I'm not going to take a whole big detour on it, but here's the story of Lorentz invariance in brief. Okay, if you want psi to be invariant under Lorentz transformation, you take psi of x into some psi prime of x prime, where I sit off the side here, x prime mu is some lambda mu nu x nu. So it's the Lorentz transformation on that. Okay. This is not a scalar, so you don't want to just make it psi of x. In general, it's some s of lambda. So the Dirac indices. This is now a 4x4 matrix acting on the Dirac indices. So the Dirac indices get rearranged. And you know that has to happen just because we know the solutions. As I boost this thing, the relative size of the upper and lower components is going to change, right? You know, P could be 0 in the rest frame and non-zero, so the lower component gets generated as you boost it. So you want that. And so if we want psi bar I d slash psi to go into psi bar prime I d slash prime psi prime, so in other words, everything primed, then you require that f gamma mu s minus 1 is this Lorentz transformation minus 1 mu nu gamma nu. Okay, so this basically allows you to make the transformation on the derivative operator to turn it into the derivative with respect to x prime. So that's the condition, and then you solve for it. Okay, so then there's a bunch of solution. If lambda mu nu starts off as delta mu nu plus omega mu nu, some infinitesimal Lorentz transformation, then by doing a series of infinitesimal Lorentz transformations, S turns into e to the minus I over 4 omega mu nu, sigma mu nu, where those are the sigma matrices. Okay, the commutators of gamma mu and gamma nu. All right, so I'm not deriving, I'm just telling you what the answer comes out to be. That's relevant for what we're about to do next. Okay. Does anyone have any questions about that? Yeah.
Delta mu nu should be a G mu nu?
Well, G mu nu with one upper and one lower is delta. And so yes. Okay. But if you think about it, if I take G mu nu G, sorry, that's a G mu gamma, let's say. Okay, so one upper, one lower. That's how you raise and lower things. That's equal to delta nu gamma. Okay. Okay, and so it's 1 if nu and gamma are the same, and you can sort of see that one of these has, you can count the minus signs? Good. But yes, you could write that one upper, one lower, because it's the same thing. Okay, so the question arises, is there any other invariant any other Lorentz invariant? In particular, you might try something that looks like the following: S Lagrangian is some m alpha beta psi alpha psi beta. Okay, so let's just ask that question. Well, under a Lorentz transformation, that goes over to m alpha beta S alpha gamma S beta. One of these guys should clearly be up, I guess. No, actually, these are not. These are just plain old Dirac matrices. So there's no up and down. Delta psi gamma psi delta. Okay. So does the question then is, can we find a matrix where S transform M S equals M? Okay. If you do that, this would then equal M alpha beta psi prime, or let's make it gamma delta, sorry. Gamma psi prime delta. Okay? If that's the case, then we found another invariant. And so it's just it becomes a math problem, a simple matrix issue. And the solution, there is a solution, is M is I gamma 0, gamma 2, which is called C because when you do charge conjugation, it's related to the charge conjugation operation, which we haven't done, but there it is. Okay? So there is a term like this, so we can write out a term which is a Majorana mass term, is minus m over 2. So I'll write it as psi transform m psi plus Hermitian conjugate is psi bar transform transform m psi, or yeah, maybe I should have used the notation C there. M is C. I don't want to confuse it with the mass itself. And that's psi bar. Okay. So I've written down the term with its Hermitian conjugate, so that's why these guys are here. But this is a Lorentz invariant, and this is not psi bar, it's psi transform, because this and that are the same thing, just in matrix notation, right? Okay. That's the Majorana mass term. Okay. One of the things that you can see is if I take psi left transform C psi left, okay, that's psi transform gamma left transform is gamma left. I have I gamma 0 gamma 2 gamma left psi, that's a gamma L, that's not equal to 0, but psi right transform C psi left is equal to 0. Okay. So this looks the reverse of the other mass term. The other mass term connected psi left to psi right. This connects psi left to psi left. So we can have independent mass terms. Since the kinetic energy piece is left to left, we can write out L is psi bar left, I d slash psi left, plus ml over 2 psi left transform C psi left plus Hermitian conjugate. And I could just stop there. I don't have to even do anything with psi rights. That's a perfectly good piece just with the left parts in there. Or I could, if I want to, I can add in psi right, ID slash psi right, plus a different mass. I want psi transpose, C psi rights, plus Hermitian conjugate. So they can have, you can have the right piece also, but it's completely disconnected, at least at this stage. The lefts and the rights are separate particles. However, we know that psi left has only half the degrees of freedom of psi, so it's only got 2 degrees of freedom. So there's 2 degrees of freedom here, and there's 2 degrees of freedom here. Instead of the 4 that we normally have. So we split them up into these separate pieces. There's no longer any symmetry. No longer particle conservation. So normally you say that the symmetry psi goes to e to the I. Alpha psi gives you a conserved current, and that gives you a conserved charge, which is particle number. Here, this is not a symmetry. Because the mass term sitting up there transforms with a phase. It's not invariant. The kinetic energy piece is, but the mass is not. So this says that there's no conserved particle number. So you can have psi plus psi going to nothing in these theories once you add interactions, of course. And so it's common to say that the Majorana particle is its own antiparticle. And you can make that a little bit more formal by just looking at the equations of motion. Okay. We're going to come back to this when we do neutrinos. We'll talk about neutrinos later on. But this is the basic foundation here. We have two types of masses that you can get: the Dirac masses, which connect left and right, the Majorana masses, which connect left and left. You can put them both in a theory. That will do that with neutrinos, and it has interesting consequences. But that's the basic Lagrangian for the Majorana star. Okay. In nature, the Majorana, the mass terms, we don't know if they're for neutrinos, if they're Majorana or not. Clearly, all effects of this disappear in the limit that gets very small. So it's a very small effect in the real world because these masses are small. But that's clearly one of the interesting questions now. Are the neutrino masses Majorana, in which case you would have a Lagrangian like that, or Dirac, in which case you'd have the old type of Lagrangian. Okay. Anyone want any more discussion of these guys? Yes.
Well, you said they could be mixed as well.
Yeah, you can have masses. So the more general case, we would have. Let's talk about psi left and psi right. You can have masses that connect the left to left. So I'm going to do a 2 by 2 matrix here. So there's M Majorana here, M Majorana here. This is M Majorana left. This is M Majorana right. Okay, those can be two separate masses. And then the Dirac mass connects left to right. So it connects it that way. Okay? And then your mass eigenstates are the eigenstates of this matrix. You diagonalize the matrix and you get then states that are mixtures of left and right as your mass eigenstates. In the standard model, we'll see later on that the left-handed one has to be 0. Okay, and that's because the left-handed neutrino is a partner of the left-handed electron, and you can't do this for an electron for charge reasons. So that guy has to be 0, but the right-handed guy doesn't, and so this goes to 0 M Dirac. Let me just Dirac M Majorana. So I'll just call it M right Majorana. And in the limit that M Majorana is big, the eigenvalues are there's the big Majorana mass and a little eigenvalue which is m d squared over m. Okay, so when I diagonalize this, there's two eigenvalues. One piece gets mixed, and so this is one of the natural explanations for why we only see in nature dominantly left-handed. This one is dominantly left-handed because it just takes a little mixture of the right particle in there. With a small mass, if M Majorana is big, then one of them the other particle sits high. This guy gets low because you have a typical mass divided by a big number. And that's the most compelling explanation we have of why neutrino masses are so much lighter than other masses. It's called the seesaw mechanism. Yeah, the old seesaw where you put the big guy up here and the little guy up there, and it tilts it. Okay, so that's the origin of that. Okay, so I'm okay. Good. Anybody else? Questions about this? It's actually a very clever thing, I think, actually, to realize that you could do that. But it's, it's not good for anything else but neutral particles that are neutral under all interactions, because of this lack of symmetry here. You couldn't do this, in QED. If you tried this with an electron, this is the thing that gives you charge conservation, and a Majorana mass term then would not be invariant under the charge operation. So you can't do it for electrons. You can only do it for neutrinos because they're neutral. All right. Okay. The next set of stuff is a little bit of technology that I want to get through. I want to do spin sums. Technology for spin sums. Let's first do the non-relativistic case. So if we had a matrix element, non-relativistically with fermions would be chi initial, chi final, some 2x2 matrix. Okay? And as always, you're instructed to, when you form cross-sections, if their spins aren't measured, you average over initial spins. And you sum over final. Okay. Average over initial because half the beam is one, half the beam is the other. Sum over final because you accept anything that goes out, so you sum over them. Okay, so we have to sum over those spins. So when we square, we take m squared, which is then chi dagger f m chi initial dagger m dagger chi final. Okay. And we're instructed to sum over the spins. Chi's can be either 1, 0 in some basis or 0, 1. And so if I'm instructed to sum over the spins, let's do it of the initial guy. I have chi initial dagger, and those are actually vectors. So let's carry the vector index along for the moment. A, B, so A is either the top or the bottom, on each case. Okay, we can do that explicitly. That's 1, 0, whatever A is, 1, 0, whatever B is, plus 0, 1, A, 0, 1, B. And so you see that if A and B are the upper index, that gives 1. If they're the lower index, it gives 1. If one's the upper index and one's the lower, you get 0 in either case. So this is delta AB, okay, which we would really write in matrix notation, sum over S, chi I dagger is 1, meaning it's a 2x2 unit matrix.
I just find the subscript A here, A component of the...
So yeah, let's A could be either up or down, the upper component or the lower component. You can do it like we do them 1 or 2 if you want. So one, in this, for this spinner, the one index is 1, and the two index is 0. This is 0 and 1 for those two, okay? So yeah, this probably makes more sense. If you sum over these guys, the direct product at the end is the unit matrix, okay? But I've had enough people be confused by that sum, by that notation, that I wanted to just do it explicitly for once. Yes.
Now we use that notation down there.
The bottom, the matrix notation. Yes.
So our space necessarily has to be orthogonal.
Well, you choose the basis. You want an orthonormal basis of the space. Yes.
So, but we have to choose one for that notation.
Well, you have to choose one in general. You know, if you're defining your basis states, you always have to choose them to be orthonormal.
But I mean, we have to choose an orthonormal basis for that notation.
Yes.
Okay.
Yes. Great. Right. And notice that this is sort of an outer product here. This is chi dagger. So this is the down. This is the matrix that way. So it's like forming a matrix out of 1, 0 direct product with 1, 0 plus the 0, 1 direct product with 0, 1. That equals the matrix, that matrix. Okay? That's what this thing means. Okay? So now we have m squared has sum over the initial spins has become chi dagger f m dagger chi, which is m dagger, dc chi c chi dagger d. Again, with this, we do the same trick again. Do the sum over the final guys. So if I sum over the final initial and final guys of m squared, it equals trace m dagger. Okay, so this turns into the unit matrix also, times this unit matrix turns into the trace, and we're done. Okay. Okay. Now let's do the same thing for the Dirac case. Okay. Here, the matrix element is going to be, let's say, u bar of p prime gamma u of p. Okay. M squared then is, okay, and is u bar of p prime gamma u of p. I've got u dagger gamma dagger, leave a little space there if you're writing it, gamma 0 u p prime. So this is actually p, and I maybe didn't leave enough space myself. Okay, I'm going to put gamma 0 there. 2 gamma zeros is just the unity. And so this then turns into u bar of p, I'll call it gamma bar u of p prime. The gamma bar is gamma 0, gamma dagger, gamma 0. Okay. Okay, so in this case, we're asked then to do spin sums that look like sum over the spins of u of p, u bar of p. That's a 4 by 4 matrix, right? So let's stick an alpha beta index on that just for the moment. But that's a 4 by 4 matrix, so alpha and beta run 1 to 4. And we can actually work out what it is. The normalization e plus m over 2e, that's the normalization factor squared. We have chi sigma dot p over e plus m. Chi, that way, chi dagger minus chi dagger sigma dot p over e plus m. That way, so that's the alpha index there, the beta index goes there. Okay. So that was the normalization factor, the way we're doing normalization so far in the course. This is the old chi's. Now, the chi sum we just did, so those turn into 2 by 2 unit matrices. So that's the sum over spins there. So this is e plus m over 2e. The upper becomes 1. This becomes minus sigma dot p over e plus m minus sigma dot p, plus sigma dot p over e plus m down there. And this becomes sigma dot p squared over e plus m squared. Let me just simplify that before going on. So alpha beta sits there. That guy is p squared over e plus m quantity squared, which is e squared minus m squared over e plus m quantity squared, which is e minus m over e plus m. Right? I take one of these and divide out that. Okay, so that's okay. This in turn gets written in the following way: is so there's a 1 over 2e that sits out there from the normalization. The e plus m's are going to cancel here. That cancels, and this one also cancels. And so we just have to write e plus m over e plus m there. Turns into then p slash plus m alpha beta. Okay, so the upper component is e, gamma 0 here, it has 1, and I forgot a minus sign here, sorry. Oops. There was a minus sign that's important. There we go. E plus m is the top index, the gamma dot p is the off-diagonal one, and then down here it's minus e plus m. Okay, so it works just like, if you know your gamma matrices in your head, you can see that. Okay, consistency says if I have p slash minus m on u of p, that had better equal 0, just because p slash minus m on u of p equals 0. And so if I take p slash minus m on this, I get p squared minus m squared, which is 0. Okay. So that works. Okay, so there's our projection. And similarly, which I won't work out, sum over spins of v of p, v bar of p is p slash minus m over 2e. Okay, so if we take this matrix element that we have there, and I sum over these spins, then this matrix is replaced by p slash plus m. And if I do the same with summing over these spins, so I bring this around, it gets replaced by p prime slash plus m. Let me write it out in one step instead of two. And if you ask questions, if you don't see it, I'll go back and do it. So sum over spins and spin primes of m squared will be trace of, now let's start with the gamma matrix there, a gamma matrix p slash plus m for 2e, gamma bar, which is the thing that sits right there, then p prime plus m over 2e prime, and you come back to the original indices, so that gives you the trace. P prime slash. The one little symbol does both jobs. P prime slash plus m. Okay, so there's spin sums for you. The things we need to know in doing this is the gamma bar. If gamma equals 1, remember gamma bar is gamma 0, gamma dagger gamma 0. If gamma is 1, gamma bar is 1. If gamma is gamma 5, gamma bar is minus gamma 5. Okay, that's one people often don't catch, but you have to think about it. Just gamma 5 dagger is itself, and then gamma 0 goes through with a minus sign. If I have gamma is gamma mu, then gamma bar is gamma 0, gamma mu dagger, gamma 0. If you work gamma 0 is diagonal, so it's unchanged, so that becomes gamma mu itself. Gamma 0 becomes gamma mu. And gamma I has sigma and minus sigma. It's anti-Hermitian, so there's an extra minus sign, but it's compensated by going through there. Again, I can work it out if you want, but it's gamma mu. Gamma is gamma mu, gamma 5. Gamma bar is also gamma mu, gamma 5. And just one. All right. Again, I can work it out if you want. And gamma is some A slash B slash up to some, let's call it N slash. Gamma bar is N slash B slash A slash. You end up reversing the order. When you transpose, you end up reversing the order anyhow, so it comes to you in the backwards order. Okay. Everybody content on that? Do you want to let me move on? Let's do photon spin sums too. Okay, this has an interesting little twist. So let's consider some matrix element. The matrix element is going to be epsilon mu. Let's make it non-script mu. Okay, so there's some matrix element that you have to do there. We're going to use the fact that this is gauge invariant. So K mu M mu equals 0 is going to be important for what we're about to do. Okay. If we pick the z direction along K, okay, then K mu is K 1 0 0 1. Epsilon mu is 0 1 0 0. It's transverse, or 0 0 1 0. So those are the two polarizations. The gauge invariance condition K mu M mu equals 0 then is K M0 minus K M3, so that whatever this matrix element is, its 0 component equals its 3 component. So now the spin sum. Okay. If I sum over the two polarizations of epsilon mu M mu squared, well, you can see this is M2. I mean, that's M1, sorry. It's 0, 1, 2, 3. M1 squared. This one gives M2 squared. So I get M1 squared plus M2 squared. Okay. So we could stop there, but let's not. The more convenient thing to do is to add plus M3 squared minus M0 squared. Okay. By adding that's 0, since I just proved that M0 and M3 are the same by gauge invariance. This then can be written in as a covariant form. It's minus G mu nu M mu M nu. Right? M mu M nu. So now it's covariant. This guy looks non-covariant, but by using gauge invariance, you can make it covariant. And so the rule becomes, even though only the transverse degrees of freedom count, epsilon mu of lambda, epsilon star nu of lambda equals minus G mu nu. Okay, and people that don't like putting equal signs when it's not true do something to show that it's replaced by that. Okay, it's not this spin sum actually is not that, but it can be taken to be that when you have gauge invariance. Okay, so it's, you can write it as goes to, or putting the dot over there means it's not really equal to, but you can take it that way. So you place it that way. Okay. Any questions about that? Yes.
Now, if I recall correctly, isn't it actually equal to minus G mu nu plus K nu, or the unit vectors?
Well, you have to be a little bit careful on that. Let's see. I think that must be right. That must be right. That's true. But that's a non-covariant form because you're dividing by the magnitude of k, which is not a Lorentz invariant. So it's sort of non-covariant. It's also technically true, but this guy should have a sort of a standard Lorentz covariance piece, and it doesn't if you do that, because you're dividing by the magnitude of the 3 vector. Okay? Yes. All right. Well, a little bit of things that I need to do. Let me quickly do traces of gamma matrices. And then maybe part of an example, and then we'll be out of the Dirac stuff. Okay. We just saw that to take matrix elements and square them, you end up with traces. So we have to get good at taking traces. So let's just give you some of the rules. Trace of gamma mu equals 0. That's pretty obvious. You just do it on all the gamma matrices. Trace gamma mu gamma 5 is also equal to 0. Trace of A slash B slash, so those are both have gamma matrices there. You can use the property of the trace to write this as trace B slash A slash, because trace doesn't matter what your ordering is, which then is 1/2 trace A slash B slash plus B slash A slash, which, if you think about that, that's the commutator of 2 gamma matrices. So it's 1/2 trace gamma mu gamma nu plus gamma nu gamma mu A mu A nu B nu. That's 2G mu nu. So this is then 4 for that's 2G mu nu times the identity matrix, 4 by 4 identity matrix for A dot B. Okay. The trace A slash B slash C slash equals 0. You can get that. It's the trace of any odd number of gamma matrices. That's equal to 0, and you can get that just by commuting things through. Trace A slash B slash C slash D slash is 4 A dot B C dot D plus A dot D B dot C minus A dot C B dot D. Okay. You prove this by anti-commuting these things through each other, picking up minus signs till you get back to the original, and then that's it. Trace gamma mu, gamma nu, gamma alpha, gamma beta, gamma 5. Okay, gamma 5 doesn't count in this odd number of gamma matrices, because it actually has 4 gamma matrices in it. It's gamma 0, 1, 2, 3, 4. So it counts like an even number of gamma matrices. This you can prove is anti-symmetric, totally anti-symmetric. There's only one thing that's totally anti-symmetric, and that's the epsilon tensor. Then you do one example. It turns out to be minus 4i epsilon mu nu alpha beta. No, it stops there. Sorry. and quickly throw up some other useful identities if you want. Gamma mu is 4, or d in general, in d dimensions. Gamma mu a slash gamma mu is minus 2a slash. You can do that by commuting it through. Gamma mu a slash b slash gamma mu is I didn't write the answer out here. So I may have to. It's a dot b times something. Is it 2 or is it? It's 4, I think. 4. Yes, it's 4. Definitely 4. So it's 4a dot b. And one that I've used a lot in my career, gamma mu gamma sigma gamma nu, is g mu sigma gamma nu plus g sigma nu gamma mu minus g mu nu gamma sigma minus I epsilon mu nu alpha beta gamma 5. Oh, let's see. I got my indices wrong on that. Epsilon mu sigma nu beta. There we go. Okay, so it's the last index goes with the gamma 5. Okay, and that sometimes lets you reduce lots of products. All right, let's do one little mini sample, partial sample. I'll just take you through the steps without doing too much of the algebra. Remember the Compton scattering. We wrote out the two matrix elements minus IM it was E squared epsilon mu of K epsilon nu of K prime starred U bar P prime gamma mu 1 over P slash minus plus K slash minus M gamma nu minus gamma nu 1 over P prime slash minus K slash minus M gamma mu U of P. All right, so given how much time we get here, let's just take a piece of this and follow that piece through briefly. So when I take m squared, I'm going to want to square m squared in forming the cross section. I'm going to want to take a half times a half out in front. This is the average over 2 photons polarization. This is the 2 electron spins. And we sum over then over all the spins of everything. Okay, so our task is to do this. Let me just call this gamma mu nu, at least for the moment. I have then the sum over the spins. So I've got a quarter. The sum over the polarization for photon number 1 is minus g mu alpha. It's going to be the sum of polarization number 2 is g nu beta. I'll have a fermion trace. I'll have gamma mu nu from that, and over here I'm going to have gamma alpha beta bar the barred one. Gamma here sits p slash plus m over e plus m from that polarization sum. Over here sits p prime slash plus m, no, over 2e, sorry, 2e over 2e prime from that. And maybe that's where I'll stop on this. And I could have some notes worked out on handling this. Maybe just one step on the notes on handling that. The gamma mu nu, this first one here is gamma mu p slash plus k slash plus m over p plus k squared minus m squared gamma nu. So that's what that is. So there's various things you could do on it. You could do various identities, but one of the first things to note is that since that's sitting next to the u bar of p, the way you handle that is you can so I keep the gamma mu k slash gamma nu. The bottom stuff is just going to be unchanged, under everything here. But then I can write the other one as p slash gamma nu plus minus p gamma nu sitting out here plus m. So I've added and subtracted gamma nu p slash. This piece can be set equal to 0 since it's sitting next to so that piece goes to 0, or equivalently it vanishes when I sit right next to that guy. And this turns into 2 p nu. So if I were doing this, I would do that step before taking the trace, and then it's just a bunch of algebra. It's a little bit painful. I'm certainly not going to do it here, but I think I've showed you all the steps to take an initial matrix element to get to a final one, aside from just sitting there doing the traces. Yes?
Now those last two terms, are they still multiplied on the left by gamma mu?
I'm sorry.
Those last two terms.
These two terms here? No, gamma nu is, oh, yes. Yes, thank you, sorry. Yes, we have a gamma. Okay, yes. But it's much easier to take these traces than it is to take all those. And so it gets rid of, so we're now down to odd numbers of gamma matrices, so you can use all the odd rules. So instead of having odds and evens both, you have odd numbers only. And so it's much easier. Anyway, let's stop there. That's the end of what I want to do on Dirac stuff. Next time I come back, I do practical group theory, which means group theory that I do in my life. Okay, so it's not going to be fancy group theory. It's the stuff we use.